Okay, so we have a problem with a uniformed rod of mass 1 and length 2 meters and kilograms, which is free to rotate about one end. So we have this little pivot here, and it's going to slide on down that way. If the rod is released from rest at an angle theta 60 degrees with respect to the horizontal, what is the speed of the tip of the rod as it passes the horizontal position? Okay, so we're going to use conservation of energy. In other words, energy initial is equal to energy final. Now your initial position will be right here, and your final position will be there. So it's mentioned that initially it's released from rest. Released from rest. In other words, there's not any, it's stationary. So the only type of energy we're really worried about is potential energy. Potential energy in this case due to gravity. And at our final position, what we're going to have is kinetic energy. In particular, we want rotational kinetic energy. So that's what we have set up, that our energy initial, which is just potential energy, kinetic energy, our energy final is just kinetic energy because it's just spinning around. It's not moving and spinning, it's just spinning. So let's set this up. We know that potential energy is mgh, which I'll just call y. And our rotational kinetic energy is 1/2 I omega squared. Okay. Well, what is y? What y really means is it's the height of the center of mass of this rod. So it's not like we have a point here. We're really interested in the center, which is maybe like there. That's the center of, that's the height we really want. So I'll try doing it this way and maybe it'll make a little bit of sense. We'll call this y. We'll call it y prime just so we're not confusing it with the y in our equation. And this is length L. Then we know that that height is L sine theta, which theta is the 60 degrees. But that gives us this height. What we want is like this height. Well, I'm sure you can imagine all you have to do is divide that by 2 to get our solution. So y is L sine theta divided by 2 because that's the height above our ground for our center of mass. Okay, so hopefully that makes sense. We have mg L sine theta divided by 2 equals 1/2. Okay, so we're going to need to know the moment of inertia for our rod. And the moment of inertia in this case is just going to be ml squared divided by 3. So that's that. ml squared over 3 times omega squared. Well, right off the bat, we can see this cleans up a little bit. We can see the m's cancel. This L will drop with here. This 2 drops with here. And we get G sine of theta is equal to L omega squared over 3. Okay. Well, let's use this fact. So the speed we're looking for is the tangential speed. Essentially, we want to know how fast this tip is going once it hits that particular point. Well, we can tell you how fast it'll be going from an angular point of view, but what we want to know is right here, even though it'll have angular velocity go this way, we want to know the tangential velocity. And we have an equation that can relate those. It's equal to just r omega. And we can think of r as just being the length of the rod. So I think it's quite clear now that if we find this omega, we can find the tangential speed. Okay? So yeah. So now that we have that, let's continue. And let's just solve for omega, and then I'll go and do like a little recap. 3g sine theta divided by L square root. That's your omega. And if you multiply it by L, that's your tangential velocity. Okay. So let me just set it up here so we can look at this for just a second and kind of I guess do like a little recap on what we actually did, and hopefully any questions you might have might make a little more sense now. So we have this rod that's sliding down, and what we want to know is how fast the tangential velocity is at that bottom part. And we know at the very top it has potential energy. It has potential energy due to gravity, which is just mgh. And we know that your kinetic energy, your rotational kinetic energy, is 1/2 I omega squared. So that was just, I put my thing to charge, but that gets you there. And then what we can do is we can try to find out what those things are. So the first thing we try to do was find y. And I think that's maybe the first part that confuses people, because you just want half the length. You want the center of mass of the rod. And the center of mass is going to be right in the middle. So that's why we had to divide that by 2. And then from there, all we have to do is set up our equation. So we have potential energy is equal to kinetic energy rotational. So there's no kinetic energy at the top because it's released from rest. And then at the bottom, you're just going to have your kinetic energy there. So then we go in and we solve for our omega, because with omega, we can find our velocity, because our tangential velocity, because it's equal to just r omega. And then just algebra. So hopefully conceptually that kind of makes sense. And